Let me announce John Maloney is a pioneering figure in creative computing and educational technology. He's best known as a co-creator of Scratch, where he spent over a decade shaping one of the world's most influential platforms for learning to code. His work has helped millions of young people around the globe explore programming as a tool for creativity, expression, and problem solving. In addition to Scratch, John has contributed to foundational technologies such as Squeak Smalltalk, eToys, GPBlocks, and the Morphic UI framework. In 2017, motivated by watching a student struggle with complex setup processes, he launched MicroBlocks to make physical computing more accessible and learner-friendly. John has a BS and MS degrees from MIT and a PhD in computer science from the University of Washington. I'm especially excited to welcome John to the summit today. He deeply cares about education and about making digital tools truly accessible for all learners. While his work has shaped some of the most widely used creative coding platforms in the world, he approaches this work as an educator. You will see that and see that. You will hear that and see that in his creative keynote today, which reflects both his curiosity and his genuine commitment to lowering barriers in educational coding. Welcome, John, and thank you for sharing with us today. You can share the screen.
Thank you so much, Liz. Oh, someone else is sharing. That must be you. Let's try that. Thanks, Liz. As I am also very, very inspired and in some ways humbled by having all these brilliant educators here. I mean, teachers are really where this stuff gets out to actual kids, and that's what I'm passionate about doing is making technology not only like interesting but fun for kids all around the world. So today I'm going to talk about this concept of tinkerability, and I'm going to show you tinkerability in Scratch, MicroBlocks, a project I've been working on for the last 9 years, and how that applies to problem solving and understanding the world around us. So before we get started, there's a link here. Maybe somebody will drop this in the chat. This is a link to my slides. That's for those of you who might want to like look ahead or look back where we were. And at the end are some links to useful resources for MicroBlocks, and there's a link to a paper that you might want to look at and stuff. So what am I going to talk about? Well, I'm going to talk about this concept of tinkerability. I don't think that word is in the dictionary. It's a word that Mitch Resnick and I coined in this 2010 paper about Scratch. And I'm going to show you how it works in both Scratch and MicroBlocks through a whole bunch of live demos. Hopefully the demos will go well. So Scratch, we launched Scratch in 2007. We started development at the MIT Media Lab Lifelong Kindergarten Group in 2006, and we spent actually quite a few years working with kids and refining it before we actually launched it. It didn't come out of nowhere. It actually grew out of two different blocks coding projects. One was in Alan Kay's research group, which I was part of at Walt Disney Imagineering, where we were creating a blocks language called eToys. And unbeknownst to us at MIT, they were creating a blocks version of Logo called MicroBlocks. Well, I heard about the Scratch project in 2002, and I said, oh, I want to go work on that. So I ended up going from Walt Disney Imagineering to MIT, and I ended up working on Scratch for 11 years. Anyway, it's fair to say that Scratch launched a sort of a revolution in educational programming languages because everybody saw blocks and went, wow, what a cool idea. While we were working on Scratch, another group at MIT, a graduate student in that group named Rika Rose Roach, created a blocks programming system in Java called OpenBlocks, that was sort of meant to be repurposed for lots of different things. In 2010, Hal Abelson, a professor at MIT, took a sabbatical at Google, and he created App Inventor along with one of his students who was at Google. And they used OpenBlocks as the blocks language for that. So it was a blocks-based language for programming mobile devices. And they used OpenBlocks, but OpenBlocks was written in Java, and that wasn't a great fit for running in the browser. So they started working on a JavaScript version of blocks. And a fellow named Neil Fraser picked up the ball and really ran with it. And he created this great blocks language called Blockly, which is now the basis of lots of things, including actually Scratch. So Scratch went back and got rebuilt on top of Blockly, years later. So at this point, Scratch has reached millions of users. As of 2024, it was 140 million. I think maybe it's over 200 million by now. It's just amazing. And Blockly also has had a huge influence, not in terms of the number of users of Blockly itself, but the languages created with Blockly. So Blockly has been cloned 3.8 thousand times, and that means a lot of blocks languages out there created with Blockly. So blocks were a big success from Scratch, but there was another aspect of Scratch that not everybody appreciated and replicated, and that is tinkerability. I would define tinkerability as a system that allows users to quickly assemble and experiment with code, electronics, mechanical systems, building blocks, whatever. You see tinkerability in a lot of tools or kits for kids. It might be like wooden building blocks, Lego kits, electronic kits like the 101 kit I used when I was a kid, mechanical kits like Erector sets or Meccano. The properties of tinkerability are the system gives you immediate feedback. For example, in electronics, you connect a battery to a light bulb and it lights up right away, or maybe it doesn't if you didn't connect it right. Typically, these kits are pretty fail-safe. You can make mistakes, but nothing bad happens. Maybe your tower blocks falls over, or maybe your LED doesn't light up. But you get to try again. There's no penalty for making mistakes. And finally, many blocks or many tinkerable systems are discoverable. So if you're playing with something like Lego bricks, you can try putting them together, and they click together in certain ways and stick. In other ways, they don't really stick very well. And you sort of discover by using them how to best assemble things. So tinkerability isn't really a new idea in computer programming. Logo, which was developed in the 1960s, was an educational language that was tinkerable. And then similarly, BASIC in the 70s, and professional languages like Lisp and Smalltalk, all of those had this tinkerability property. I want to show you kind of what I mean by tinkerability by actually doing something in Scratch. I'm going to just close that little tutorial window. So most of you have seen Scratch, but I'll just review. Over here, we have the stage, which is where you build your project. You put media in there and make it come to life with scripts. This cat is a little sprite that you can control with scripts. And then over here on the left, we have a palette of different scripts, and it has all these different blocks. It was very carefully selected commands so that there weren't too many things. You don't want to overwhelm the user. And then the command names have useful names or self-explanatory names like move 10 steps. And you can just click on one of these to see what it does. So this is the discoverability aspect. So that moves, and this turns the other way. So I already, just from playing with those a couple of blocks, I have this idea for a game. What if we had the cat move back and forth, maybe using the arrow keys, and meanwhile, like things are falling down like pieces of food, maybe I don't know, fish and chicken and other things that cats like to eat. And the cat is trying to catch them to get points. So I've already got a good start. If I just move, I'd like the arrow key to make it move to the right. So let me see. There's an event here that says when the space key is pressed. So I'll say when the right arrow key is pressed, move to the right. So let me drag him over here, and oh, sure enough, that works. So I could duplicate this, and I could make him, when the left arrow key is pressed, move to the left. And so now I have the beginning of my game. So I never had to wait for anything to compile or download or anything. Everything just worked. As soon as I made the script, I could try it out. So I've got it moving left and right, but this gives me this idea that I don't think I like the way when it goes to the left, it doesn't look to the left. It looks weird that it's backing up. So I'm going to look to see if I can change how that works. And if I go to the motion category here, I notice that there's a point and direction block. So let's try that. And there's a cool little compass thing. So let's say that when I press the left arrow, I'm going to point in the left direction according to this little compass thing, and then move. So I'll press the left arrow now. Whoops. So it's not doing what I was hoping it would do. It's moving to the right. It's turned upside down. But one thing is right. It is at least looking to the left, which is what I wanted. So let's see if we can fix those other problems. Well, first of all, it's moving to the left. So what if I change this to 10? My theory now is that it goes forward in the direction that it's pointing. So it's looking to the left. So now if I say go positive, it goes to the left. It's still upside down. Let's see if we can fix that. So there's a block here that says set rotation style. And let's try the left arrow again. That fixed it. So the left-right rotation style makes him flip left and right, but he stays right side up. Now let me try the right arrow. Oops, another bug. So when I press the right arrow, he's going to the left, and that's because now he's pointing to the left, and we had it move 10. So that's another bug, but I kind of know how to fix that. I'm just going to throw that away, duplicate those blocks, and make a couple of little changes here. So I'll make it point to the right, and I think now it will go to the right and it will go to the left. So I've got the start of my game. I've got the cat moving around, and I would then go on to add fruit falling, and I'd sort of debug it in a similar way. But you can kind of see that the neat thing about this tinkerability is that one thing leads to another. And when you make a mistake, it probably gives you an idea for how to fix that mistake. It never breaks. So that's another property, this safety. So let's say we tried to do something crazy like making the cat go really far. Well, we observed a lot of users doing things, and we found that sometimes their sprite would go off the screen if they made it go too far. So we added a sort of a guardrail for that operation so that it goes mostly off the stage, but you can still see the tail and drag it back. And there's other operations like the clone operation, which in our first iteration of that, people would sometimes write a program that went out of control and made zillions of clones, and the whole system would grind to a halt because there were too many objects to deal with. Sometimes it would run out of memory. So again, we put guardrails around that. And gradually over time, we made Scratch a very safe language so that you can experiment without worrying about possibly making any problems that are difficult to get out of. Okay, so after I worked on Scratch for a while, I went to a conference. I left this Scratch team after about 11 years, and I went back and worked for Alan Kay again. And I attended a conference in Seattle, the SIGSE conference, Special Interest Group in Computer Science Education. And there I saw a presentation about the microbit, which was a new thing at the time, created by the BBC to help kids in the UK learn about technology. And I thought it was brilliant. I thought it was the coolest thing I'd seen. I have to confess that when I was a kid, electronics was one of my hobbies. So here was the microbit, which was combining two of the things I love, code and electronics. I went up to the presenter, Sue Sentence, and I said, I really love that presentation. I love the microbit. I think it's brilliant. And she said, really? Well, here, take my microbit and do something cool with it. So I immediately went home after the conference, and I was staying with some friends in Seattle who had a 14-year-old daughter. And we sat down and explored the microbit using MakeCode. And we made the LED do things and buttons do things, and we explored the sensors. Yes? Question? No. Okay. We explored sensors and so forth. And after about an hour, she said, well, that was really interesting. I've got some other things to do now. And I was actually surprised, because in all of our testing of Scratch, that really hardly ever happened. What usually happened was kids didn't want to leave the computer. They always had one more idea they wanted to try, and you'd sort of have to kick them out if it was the end of the session. So I thought about why was this different? And the reason was that every time we made a change to the program, even if we just changed one parameter in one command, we had to download the program as a .hex file in those days, and then drag it over to the microbit. The whole process took like 20 or 30 seconds. And after doing that like 20 times, she was just bored with the whole thing. In the process of that 20 seconds, you sort of lose your thread of thought. So it made me realize that this tinkerability was really important. And I decided to create MicroBlocks with Scratch-like tinkerability for the microbit and maybe other microcontrollers. So what is MicroBlocks? First of all, it's free. It's open source. It runs everywhere pretty much. It runs in Chrome and Edge browsers. There are downloadable apps for all the major operating systems, including mobile devices. It's super easy for beginners, just like Scratch was, but it's powerful enough for experts to do cool things with it. It's portable. After the microbit, we started adding other boards, and it now runs on over 80 boards in addition to the microbit. And it's flexible. You can we have over 200 libraries for all kinds of different external devices you can plug into microcontrollers. So with that, I'm going to dive into MicroBlocks, and the theme of this exploration is exploring the world with MicroBlocks. So so I'm going to focus sort of more on sensors than output devices in this presentation. So when you start MicroBlocks, let me show you the microbit. So here's the microbit, and the first thing, of course, you have to do is plug it in. So I'm going to plug in the USB cable. Which way does it go? That. And you notice a few letters showed up when I first plugged it in. You can, I'll talk about those in a minute. But the next thing I have to do is I have to tell the programming environment about the microbit. So I'll select the microbit here and connect to it. And when I do that, this connection icon turns green, and it knows now that it's a microbit it's connected to. And in this palette here, we have some commands like display. So if I click this, you'll see a smiley face appears. And if I click clear display, it disappears. I can plot and unplot a point, or display a character, or scroll some text, stop the scrolling. So just like in Scratch, you can you can discover what things do just by clicking on them. I'm going to try clicking on this tilt X block, and it's giving me a number in a little talk box. I'm going to try moving the board a little bit, and there's a different number, -56, and here's a positive number. But I'm getting a little tired of clicking, so I'm going to make a little program that does that for me automatically. So I'm going to have it say over and over the tilt X, and now I can see it goes to big numbers on that side, and it's kind of close to 0 in the middle. And if I tilt it this way, it's negative numbers. So that gives me a sense of the sensor. But there's another way to sort of visualize what's going on, which is I can graph the output here. So let me open the graph window and make it a little bit bigger, and also set the 0 to the middle. So so here's the output of that tilt, and when I hold it level, it's pretty close to 0 here. If I tilt it this way, you see that it goes up to positive numbers. And if I tilt it this way, it goes to like -100. And if I sort of wiggle it up and back and forth, it sort of wiggles. If I shake it, I can make it wiggle fast or shake it slow. So you get a really good sense of what this sensor does just by experimenting with it and looking at what the graph is doing. But there's other sensors that you can use. So so for example, there's this magnetic field sensor. So I'm going to drop this block in here, and you'll notice that I can change this script even while it's running. It just keeps running. So the magnetic field is got a bigger range. So I'm going to change the scale of this graph a little bit. Now you might think that the magnetic field would just be 0, but it's not 0, and it changes a little bit as I move the microbit around. That's because it's picking up the Earth's magnetic field. It's a super sensitive magnetic field sensor. My friend and colleague, Bernat, wrote this cool program here, which, whoops, I didn't mean to drop it in there. So this is a sort of a Geiger counter program. I hope you can hear this. Should be a little clicking sound. And so this clicking sound is of course, it's not picking up radioactivity, it's picking up a magnetic field. But as I move this, I have this refrigerator magnet here. And as I move it closer to the microbit, you can hear, and you can certainly see on the graph that the magnetic field strength is increasing. Looks like a Lego piece, but it has 3 little magnets in the bottom. That's why it's doing that. So when I was playing with this Geiger counter program, I accidentally put my microbit close to my Macintosh, and it started doing this. The magnetic field was like really increasing, and I went, whoa, what's going on here? And then, of course, I realized what I have is a PowerBook. It has a magnetic catch in the lid, and it was picking up the magnets that were in that catch. So that was it. It's all I can say is it's a good thing we don't use floppy disks anymore, or I probably would have ruined quite a few of them. All right, there's one other sensor that I want to quickly show you, which is the microphone. And so there's a loudness block. I'll just drop that in here. And you'll notice this little LED comes on when the microphone turns on. So let's graph the magnetic field, and the sound level. I'm going to go back to putting the 0 at the bottom of this graph. And you can see that as I talk, you can see the sound level going up and down. Let me turn off the Geiger counter. As I talk, the loudness goes up and down. And if I put this down and I clap, you can see these big spikes. In fact, they go way above the level of my talking. So I have another program here, and let me make that a little smaller. There's a block here that counts the number of claps. Actually, let's try that by itself. I'll just click it, and I'll clap, say, 3 times. So what that's doing is it's looking for these peaks. It's counting how many peaks. It waits for the first peak, and then it keeps counting until there's a gap in the clapping. Let me try a different number. Oops, I forgot to click the block. Okay, that was 5 claps. And we can use the clap count in a program. So I'm going to run this clap input program. So let's say we wait for claps, and 1 clap will clear the display. 2 claps will show a check mark, and any other number will show an X. That's what this program does. Let's move that over there. So here's the clap program. So I'll run this, and I'll clap 3 times, and we'll see if we get an X. So we got an X. Let me do 1 time to see if, it cleared all by itself just because my voice went above that threshold. Let me clap twice and see if we get a check mark. So the cool thing about this program is you can pretend that you have a voice activated thing. So I can say clear. Oops, it did it already. Check mark. And it made a check mark. Make an X. And we got an X. Clear. So it's fun. It's only using loudness. It's not really recognizing anything. You have to pick your commands very carefully to have the right number of syllables, and then you have to yell at the microbit. But it's kind of a fun little project. Alrighty, so far I've been just using the microbit by itself, and but now I actually want to use the microbit with. I want it to be more sort of self-contained. So I want to use it in a wireless mode. So it's still a microbit, but this time now we have 3 batteries, a battery pack with 3 batteries. We have some places to plug in sensors that I'll use in a minute. And but for what I want to show you right now is kind of involves throwing it in the air. So what I'm going to do is put a rubber band around it to hold the batteries in, because I've discovered that without doing that, the batteries will fall out sometimes, and things don't go very well. So let me see here. I'll just, I think, make a new. Where's my? I thought I had a script for this. I do have a script for this hidden behind there. Okay. So what I'm going to do is I'm going to throw the microbit up in the air, and I'm going to have it collect, graph the data. First, I have to connect to the microbit, and I'm going to do that using Bluetooth. So when I turn it on, you'll see these letters WNG appear somewhat behind the rubber band, and I'll pair with it. So now it's going to the programming environment will be talking to the microbit. Oops, I turned it off. We'll be talking to the microbit via Bluetooth, and so I can still get data to graph, and I can I'll change the program and so forth. Okay, so when I press the B button, it's going to start recording, and I'll throw it up in the air. You can don't look at the screenshot, but look at my camera feed. So I'll press the B button, throw it up in the air, catch it, and press the A button. And now let's look at what we captured with our graph here. So let's normalize the scale. So it was around 100. I was moving my hands a little bit. And then when I threw it, there was this acceleration. So there's a spike here. Then as soon as it left my hand, it goes down to 0 acceleration. And you can sort of think of that as being in free fall. So it's falling as fast as gravity is pulling it down, and nothing is pushing against it. So as far as the accelerometer is concerned, there's no acceleration. It really is actually accelerating, but it doesn't feel acceleration. And then when I catch it, there's a big spike in the acceleration. And then as I hold it steady, it goes back to 0, 100, sorry. And 100 is like 1G of acceleration. So that's kind of cool. You can actually experiment with the real world and free fall. This is a lot like what astronauts experience when they go in the 0G airplane, which it flies in this it goes into this dive where it's falling as fast as gravity wants it to go, 1G down. And they float around inside the cabin as if they're weightless. And that's good training for being in orbit where they are also in free fall. I'm going to open another project now and look at some other phenomena. So as part of this project, I'm going to plug in a device. It's a very simple thing, which is just this single LED, and I'm going to plug it into the pin number 1 here on the back. When you plug something in, you have to pay attention to the letters. It says 1, that's pin 1. V is volts and ground. So you have to basically make sure you put the ground wire, which is usually black or brown, to the one that says G. So my mnemonic is black and brown go to G for ground. So I just wanted to blink an LED. So I have a program here. I'm going to start it running that turns this LED on and off. And I'm using a variable called delay to control how much time there is, how much time it stays on, how much time it stays off. And I have a second script that's running in parallel here, which tells me what the current delay setting is for the whole cycle. So it's 2 times the delay. So this is one flash per second. And what I want to do is by pressing the A button here, I'm going to increase the flash rate. So now it's a half a second per flash, 2 flashes a second, 4, 8, 16. And now it probably, for you, it looks solid. To me, it's still flickering slightly. This is 30 flashes a second, roughly. And now it's flashing at 60 flashes a second. Oddly enough, the camera is picking up a little pulsation, but to my eye, looking directly at the LED, it looks like it's lit solid. So this is basically demonstrating something called the flicker fusion threshold, which is the point at which your eye starts merging together flashes of light and starts seeing it as a continuous light. And for different people, it's at different places. For most people, it's somewhere before like around 60 times a second, it starts looking like a continuous light. But some people are more sensitive and they'll see flicker even up to 70 or 80 or 90 flashes per second. But if I go faster here, like now it's flickering at 500 times a second, and I didn't see any difference between 60 times a second and 500 times a second. but our ears are more sensitive than our eyes. So I'm going to try using our ears. So first I have to show you that hopefully you heard a little click here. This block, pin 27 is the speaker on the microbit. And so when I turn the speaker on, it pulls the diaphragm and that makes a little click. And then if I turn it off and turn it on again, I may get another click. So what I'm going to do is I'm going to temporarily turn that off, and I'm going to put these blocks into this program. So every time the light turns on, I'm also going to turn on the speaker. Every time it turns off, I'll also turn off the speaker. And so we should get a click for each flash. Let's see if that works. So you should be hearing a click every time it flashes. And I'm going to press the A button to increase the flash rate. So to me, it's still flickering a little. Now it looks solid, but it sounds like a motorcycle. And if I keep increasing it, the pitch of the sound goes up. So my ears are picking up as pitch, are picking up these different time scales. So these are different pitches. And that's really neat. Our ears are more sensitive to time in certain ways than our eyes. And so we can use our ears to help us understand the world in ways that our eyes can't tell us about. I'm going to use that idea in another way. So the lights in my house, and probably in your houses too, are LED lights. So it makes me wonder if actually maybe these LED lights are flickering. And let's see if we can figure out if they are using this sensor. This is a photo transistor, which responds to changes in light fairly quickly. And let me open another project to explore this light phenomena. So I'm going to plug this light sensor, this photo transistor, into pin 1. Again, making sure that oops, I missed one. Making sure that the brown wire is connected to G for ground. And let me just, before I do anything else, let me get this analog pin block and see if I'm getting some data here. So it says 300, and let's see if I cover this with my thumb. It's a much smaller number. So it looks like I am picking up the light. And I have this program here that it's going to collect data and put it in a list. It's going to collect readings from this analog light sensor and put it in a list. And then when it collects all of them, it's going to graph them. So I'm collecting it separately than graphing, because the graphing takes a little bit of time and slows the process down. And I want to get higher time resolution than what that would allow. So let me reposition this graph a little bit and clear it. So I'm going to run this program and let's see what happens. Oops. Let's put 0 in the middle. And I think we have to decrease. Okay. So now I'm starting to see actually 0 in the middle wasn't helpful. 0 at the bottom is more helpful. So now I'm seeing a sine wave, that's interesting. So it does look like the LED is blinking. And let me do that one more time. Yeah, and the center of the sine wave with this particular angle of the sensor that I'm holding, the center of the sine wave is at 250. So that's interesting. So let's see if we can sort of change that into sound. So if I say, if I make the speaker turn on when it's above 250 and turn off when it's below 250, then we should get some kind of a buzz sound. And so I'll try this script. And hopefully you can hear a sort of a buzzing sound. Let's see what the frequency is. My guess would be this is a nice sine wave. I know that the AC power is a sine wave at 60 cycles per second. So let's use this script here to see if we can measure the frequency. What this script does is it 100 times it waits for it to go above the threshold and then below the threshold. And then it uses that time to compute like how many cycles per second we're getting. So I'll run this. Oh, I have to change the threshold to 250 here. Let's try running that again. So it says 120. Is that right? It seems like it should be 60. Maybe there's a bug in my program, but I can sort of test that by using my ears to compare that sound with well, I thought it should be 60. So let's see if this sounds the same. That doesn't really sound like this. Let's try 120. So this is noisier, but it sure sounds like about the same pitch as that. So for some reason, the LED light is flickering at 120 times per second, even though the AC power is 60 times a second. I actually have no idea why that is, but it's interesting. So that was kind of a real science experiment. Well, looking at flickering lights makes me think of yet another thing that we could explore, which is infrared remote controls. So I'm going to open another project, and we're going to do the same kinds of things, but with a different sensor. So I'm going to plug in this sensor. So this is an infrared receiver sensor. It's sort of an infrared phototransistor, but there's some other electronics in it that help it block out ambient light like sunlight. And in this case, I'm going to plug it into pin 0 because that's what my script says I'm using. And let's just try it out with this remote control here. Oops, let's do it this way. So if I press this, you see there's a little LED, a little red LED, visual LED that lights up. That shows me that this is actually receiving something. I haven't started running this script, but let me take the output from that LED and use it to control the speaker, just like we did with, just like we sort of did before. So you'll hear a click. Now, if I hold this button down, you hear a click followed by a beep, a little beep, followed by a bunch of clicks. That's the clicks are the repeat signal. So if you're doing like volume up on your remote control, first it says increase the volume, and then it sends repeatedly as you hold the button down, do it again, do it again, do it again. And that's how like infrared remote controls work. So I want to like look into this a little bit more closely, just like we did with the LED light bulb, and graph the results. So here's something that collects the data and graphs it. So let's clear this graph.
John, we have about 5 minutes.
Thank you. I'll go ahead and press a button. And here's the signal we're getting. Oh, I didn't hold it down very long, so it didn't repeat. Let me do it again and hold it down so it repeats. So you see that there's kind of this initial command or burst of data, and then there's repeat signals which are much shorter, and that was like intentional when they were building infrared remotes. I'm going to actually leave that running so you can hear what's going on one more time. Run this script so you can hear it. So there's the chirp, and then there's a repeat. I want to just focus in on this, and Liz, I'm getting very close to being done. So one more little experiment. I just want to zoom in on this a little bit, and I'll press this one of the keys here, this top left one, and we'll see in more detail. There are like narrow pulses and wide pulses, and you'll notice that there's a bunch of narrow ones, a bunch of wide ones. A little like narrow wide, and then a bunch of narrow ones and a bunch of wide ones. That was for that particular key. Now I'm going to press a different key. And now you see the pattern is a little bit different. There's a bunch of narrow ones and a bunch of wide ones, and then there's narrow, wide, narrow, wide, narrow, wide, wide. and then another wide, narrow, and so it's a different code. And MicroBlocks actually has a library that can decode those pulses and return and tell you which key was pressed on the remote control. All right, well, with that, I'd like to sort of wrap up. So my conclusions are that tinkerability is fun. I hope I've convinced you of that by all these demos that I did. I think it's just interesting to explore the world. It's interesting to get results right away. It's fun. It was fun in Scratch, and it's even more fun in MicroBlocks. Quick feedback supports creative flow. Like one idea just leads to another, and you can try them out right away. And you don't have to. You're not tempted to go read email because you have to wait for 2 minutes for something to compile and download. I wish that my everyday life when I'm programming in C++ to make MicroBlocks also was immediate and tinkerable, but I end up having to wait for compiles a lot. But I hope our users of MicroBlocks don't have to do that. Finally, tinkerability encourages curiosity and engagement. And thank you very much. Here are some links that you can check out. There's a paper here which talks about tinkerability among other aspects of Scratch, things that we thought were successes in our design of Scratch. And that's about it. Are there any questions?
Thanks, John. We did have a question that came up 3 times during your demonstration. And by the way, nice job doing live demos. They always make me nervous when I do them, but I always love to see other people do them. So thanks for that. But the question is, what is the age recommendation for starting kids in Scratch and then kind of progressing to MicroBlocks, or is that a progression? What's the age you recommend?
Well, I would say you can start kids with Scratch pretty young. I mean, as young as I mean, some people have started their kids when they were in kindergarten. It usually helps if they can read what's on the blocks. So kind of reading level is more of a prerequisite for Scratch than age, I would say. I have used MicroBlocks with kids as young as 3rd grade. Actually, I've used it with younger kids at like science fairs. Cambridge has a science fair every year, and we set up a booth and kids would come by. And really young kids, they don't program, but if they're sitting with their parents and their parents make a program that like scrolls their name across the screen, and when they push a button, they love interacting with the microbit. And so you can kind of introduce the idea of programming even before they can write programs themselves. But I would say 4th grade is a probably good starting point for MicroBlocks. And then it could go all the way up through college because you can do very sophisticated things with it. What I do find is that many kids, when they get to high school, they start thinking that they should be programming in a text-based language like Python or JavaScript or something. And so they kind of check themselves out, even though they don't really have to. And they check themselves out of blocks languages. So, I think the sweet spot is kind of like 4th grade through 9th grade, something like that. And if you can convince the kids that it's useful in high school and that it's not like a baby language, then they can use it in high school as well for robotics and stuff. And we have gotten reports from teams in China who have entered robotics competitions and won the top place using MicroBlocks and sort of beating the people that were using C++. I think because they could tinker with their code and make their robots work, they could improve their programs much faster with the tinkerability of MicroBlocks.
Wow, that's amazing. Having running a robot on MicroBlocks is pretty cool. John, we really appreciate your sharing with us this morning or afternoon or evening or whenever it is for everyone. Thank you very much. I posted a link to John's talk in the chat, and all of his links are embedded within that link. So check it out if you want to check out any resources that John shared. Again, really appreciate your time today, John. Thank you so much for joining this community and sharing.
It's been my privilege, and I hope you all will go home and give MicroBlocks a try.
Great. Thank you so much.